Hi, this is Zihua Liu from Tokyo Institute of Technology. Today I'm glad to introduce our paper, Global Occlusion-Aware Transformer for Robust Stereo Matching. Currently, stereo matching algorithms face the bottlenecks of ill conditional regions. One of them is tetherless or receptive regions, where they show homogeneity in the RGB domain, which is difficult for CNN-based method to extract distinguishable local matching features. Another bottleneck is occluded regions, where are regions visible from the left camera but invisible from the right camera. Such regions cannot directly estimated by matching, which may cause wrong matching and bad disparity performance. Our motivations lies in that disparities which in a bounded region, for example an object, should be continuous, which means that we can leverage restricted global spatial correlations as a guide to alleviate matching ambiguities and refine disparities in the occluded regions using the attention mechanisms. We can get the global correlations or long-range dependencies by performing the attention calculations from the stereo pairs. Then we use occlusion maps as a scope indicator to restrict the global attentions for occlusion-aware disparity estimations and refinement. This is overall network architecture of our proposed GOAT, which is short for Global Occlusion-Aware Stereo Matching Transformer. In the whole network, we decoupled the stereo matching pipeline into two processes. One is the global matching for non-occluded regions, which is indicated as a green PDO module in the figure. We estimated initial disparities and the occlusion map. The other is the disparity refinement module for occluded regions, which is indicated as the red OGA module. This module can refine the disparities at occluded regions using restricted global correlations. Next, we will briefly introduce how the partial disparity and occlusion estimation module, the PDO module, works. Firstly, we use self-cross-alternating module to extract global context informations and positional bias. The alternating self-cross-attentions modules can fully aggregate the information of the left and right fixtures, resulting in a more representative and distinguishable fixtures. After that, we conduct partial cross-attentions between the left fixtures and right fixtures and get two cross-attention matrix C-attention1 and C-attention2. Finally, we regress the initial disparities and occlusion mask using the given formula below. This page shows the visualization estimation response for the disparity candidates using proposed PDO module. Compared with the conventional cost-volume-based method, the orange one, our PDO module, the blue one, can alleviate matching ambiguities in tetherless regions by showing a single peak waveform response. After we obtain the initial disparities and occlusion masks, we further propose an iterative occlusion-aware global aggregation module, which is short for OGA. As we can show in the picture, the OGA module aggregated the local fixture with a global attention map to extend the receptive field to formulate a global fixture. Then, an adaptive fixture is formulated with a combination of the global fixture from the occluded regions and the local fixtures from non-occluded regions. For the disparity refinement, we follow the same strategy as Reft Stereo by introducing a GRU module to iteratively refine the disparities using the adaptive fixture to get the final disparity map. Here are some visualization results of the global attention distributions of the occluded regions. As we can see from the attention map, the global attention value is bigger where the features are within the same object or context. These attentions can help us formulating better features for disparity refinement. To verify the effectiveness of a proposed network and its modules, we conduct massive experiments of multiple datasets, including SceneFlow, KITTI, and Middlebury. This table shows aggregation studies of our method. We compare our proposed PDO modules with other disparity estimation methods, such as STTR and cost volumes. As described in the table, our methods shows less errors and better performance no matter at the core regions and at the occluded regions. Besides, we also conduct comparison experiments with other disparity refinement modules, including Reft Stereo and GMA. Experimental results show that our proposed OGA demonstrates better performance by showing a lower EPE and P1 value. Visualization results below also shows that together using the PDO and OGA modules can produce the best disparity estimation results. Our methods achieved top performance on the SceneFlow datasets, both as overall regions and occluded regions, as we can see from the table and figure. As for the KITTI dataset, our proposed GOAT demonstrated competitive performance with other SODA methods and ranks first in the foreground regions. Visualization results on the right also indicates that, compared with other methods, our proposed GOAT can estimate more continuous disparity results at the occluded regions, which bounded with a red bounding boxes. We further present the generalization performance on Middlebury dataset and since using SceneFlow pre-trained models, as well as the fine-tuning results on the Middlebury dataset. As we can see from the table, our proposed GOAT shows superior performance both in the occluded regions and non-occluded regions compared with other SODA methods. And this page shows that how the OGA modules use global attentions to refine the disparities in the occluded regions. As we can see in the figure, with the increase of the iterations, the disparities in the occluded regions become better and better, which demonstrates the effectiveness of our proposed method. So, for the conclusion, in our paper, we have proposed a novel attention-based network called GOAT that will estimate the disparities at the EU continental regions. We propose two specific design modules, the PDA modules for global disparity matchings and OGA modules for occlusion-aware iterative disparity refinement. Finally, multiple experiments show that our methods achieve outstanding performance on multiple datasets. For more details of our paper, please refer to the project page. You can scan this QR code for more details.